Hello, everybody. Thanks for coming out. My name is Patrick Huck. I'm a computer systems engineer at the Lawrence Berkeley Lab near San Francisco. I work on the materials project, which I'll introduce today, and thank you to Datadog for giving me the opportunity to speak here. It's been a while since I've been out and about. I'm by training a high-energy nuclear physicist, so I kind of switched path after my PhD to material science and ended up being a software engineer in material science. So pretty broad. I've been traveling around science conferences. This is my first AWS Summit and tech conference, so I'm pretty excited about that. I'll be talking about how we underwent a data and compute transformation at the materials project using AWS. Just a quick word on the agenda. I'll introduce what materials project is, talk about the choices we made for cloud architecture and continuous deployment, and then at the end talk about how Datadog has helped us a lot in terms of monitoring our cloud service. Okay, so the first part is going to be a little scientific. I'm just going to give you an overview of what data we have and what we do. The materials project is a materials science platform. We use supercomputing and state-of-the-art electronic structure methods to generate data, materials science data that researchers across the world can use. And we provide that on an open web platform. And the ultimate goal is to predict materials and develop novel materials, design novel materials for next generation applications. Our website is at materialsproject.org, and all our source codes are open to the public too. We started in 2011 as a White House initiative, so part of Materials Genome Initiative. There was the Human Genome Initiative, and kind of with that same idea, we're now trying to cover the entire materials space and do the combinatorics so that we can find new materials by using the computer instead of doing it by try and error. The goal was of that initiative to be faster, less expensive, and more predictable with materials design and materials prediction. When we started, we kind of were in this, When we started, we were in this kind of Edisonian approach of, hey, a scientist kind of comes up with a structure or a material, they kind of try to synthesize it, they do the measurements, they run the analysis and see whether it actually works for their application or not. And you go through try and error that for various different structures that you can come up with. And in the end, you might actually find the holy grail and find a structure that works for your application. What we've done with the in silico approach, so in the computer, is basically take all these structures and any others that you can come up with, run them through the computer, throw away the ones that don't really fit into your application, are not good, maybe might not be synthesizable, and then all the material scientists would have to do is take a few candidates, synthesize those, do the measurement, and get there quicker. So as I said, we're a database of inorganic crystalline material structures and their properties. We try to accelerate materials discovery, and we basically use our computations to make data-driven predictions, and then in the end also develop design tools that the larger community can use. So as you can see, since 2011, we've grown quite a bit in terms of the number of database entries. We have over 200,000 registered users, 146,000 unique materials. That comes down to over 100 million CPU hours per year to get to 146,000 unique materials and their properties. In terms of the properties, it's not only the crystal structures that we calculate, we also calculate the band structures, density of states, X-ray absorption spectra, charge density. So those are all very fundamental, important properties that come into play for materials design and materials development. All of our information, everything that we calculate, we provide for free in our open data platform. So we basically have materials explorers. You can see a little periodic table with filters on the side and a list of apps that serve certain purposes and that basically allow our users to use the data that we've generated to kind of explore their interests and explore the science and kind of get to results that they would have to calculate themselves usually. But with Materials Project, they can now just go online and basically look things up and use our platform to for their research. So our website is basically provides these apps to search and explore. Each material has its own detail page with the properties on it that a user can see what exactly the properties were. And we also have a RESTful API that allows users to pull our data programmatically and do analyses on top of it. So you can see that this drives a lot of secondary research. As I've said in the previous slides, I think we have over 19,000 citations now. So what does such a cycle look like? Basically, we'd start with structures. That's what structures basically in a material science sense look like. Feed them into a screening funnel that Materials Project provides, and we could basically apply screening criteria for the application that we want to look at, and come out with a few candidates that we can either are already the best solutions and we can go and synthesize, or we can actually also generate like a machine learning feedback loop where we take those structures, look at the ones that worked, maybe come up with models of new structures that could also work and feed them back and see if we can iterate to find the best fitting candidates for an application. Examples for the materials research that these materials are being used for ranges from all like magnetocalorics, piezoelectrics, batteries, their electrode materials, their electrolytes, also transparent conducting oxides, which is in photovoltaics or touch screens, photocatalysis, and the range goes on and on and on because it's all the materials that we have are pretty fundamental to a lot of applications. I could just quickly go through a few screenshots of our now legacy web page and show what all these properties for a single material look like. So this is for aluminum oxide, for instance. That's one material on our platform. We provide the calculation summaries, which is the output of our millions of CPU hours. The electronic structure is all interactive. Photon dispersion is one thing. X-ray diffraction patterns. You see there's a pattern here of how we kind of provide scientific data in an interactive form over a wide range of materials. And all of this is done for all of our materials with workflows and other things, as I'll explain later. People could look at substrates and kind of find materials that they can grow films on. They can look at similar structures. Basically, maybe I'm looking at aluminum oxide, but I'm interested in another one that is close by. Elasticity, piezoelectricity, which are tensors, basically describe the shear momentum, the shear modulus, equation of state. So anybody from materials of science or material science background would see those things as very fundamental to a material and be interested in it. And then one last thing I want to mention on this is that we also opened up to user contributions. So we have a platform developed that we call MP Contribs, and basically users, domain experts from different scientific domains are coming in and contributing their data to Materials Project. So it helps the community to expose their data to our 200,000 users that could basically use that data for other purposes or and basically contribute back data that is meaningful for the community. So what does, just to dig a little deeper, what does the science and DevOps processes in Materials Project look like? We have workflow software that runs our simulations. We call them Atomate, Custodian, Fireworks. Those are basically tools that take the simulation input that we set up and deploy or run them on supercomputing platforms, queue the calculations, and keep track of how the calculations are proceeding. Internally, they use the analysis library called Pymagen. It's been around for 10 years and it's become basically the de facto material science Python library to do analysis. It basically defines the structures, it defines elements, it defines band structures, all the objects and analysis tools you'd need to do material science. And then once we have our calculations basically completed and run, we wrote what we call builders. They basically take the raw data and produce derived collections, derived MongoDB collections with the data that is more relevant for dissemination later. So you can see that during our building process, we basically also push our data out to other platforms like Nomad. It's a materials discovery platform that has our raw data. We get digital object identifiers for our materials, and we disseminate it through our website, which all of this kind of makes us a pure data resource, a DOE pure data resource, which means that we are good stewards of data. We had to fulfill certain requirements. One of them is DOIs on our data products, and so that kind of got us on a short list of pure data resources. Internally, we're relying heavily on NERSC, which is the computing center at the lab, for storing our raw data, for long-term HPSS tape storage, and also for on-premise MongoDB databases. So MongoDB is very central to our entire workflow. All these workflow tools and builder tools all communicate through MongoDB in terms of managing the workflows and managing the builder processes. We rely on GitHub as part of kind of initiating either builders, but also initiating continuous deployments to the cloud, where, as I'll say, I'll introduce the MP stuff in a second, but we have a very small team, but the setup we have here, we're basically able to maintain with a small team of like 3 or 4 people. And then part of the MongoDB data that we have on-premise at NERSC makes its way on the sorry. Part of the MongoDB data makes it onto Atlas as a managed service for us, and the Atlas MongoDB through our API drives the website. So this is our team. This is basically all of Materials Project. Christine Pearson is the director with Anubhav Jain, and we have a whole side of professors and principal investigators that do the material science. Each of these green boxes has a swarm of postdocs and grad students around them. So does Christine. The core MP team, Christine plus the computer science and operations team. As I said, there's effectively 3 to 4 people here that do the heavy lifting for the material science, and it's gotten more and more difficult with the increased demands of uptime, of quick deployments, and so on, that we had decided to move to the cloud and enable us to move quicker and scale better. The goal was basically what you've seen so far was our now decade-old legacy website that is kind of one monolithic stack, and we've microserviced the entire stack and went through a process of modernizing it, and out came what we call our NextGen MP website at nextgen.materialsproject.org. We're about to make it public for the world, and we've relied on Plotly Dash to write this, to write a lot of our interfaces. The reason here is a little specific to science, I feel, because all our, as I said, our postdocs and grad students, they live in a Python world. We don't have front-end engineers much, so, and this would also be way too expensive for a science project to hire a swarm of front-end engineers and developers. So we want to use the bandwidth our grad students and also our domain experts that contribute data to Materials Project have, and let them develop their own interfaces for their own app, because they're the experts, they're the best people to write the apps. And that's where Plotly Dash comes in. For people that are familiar enough with Python, it becomes pretty straightforward to write an interactive app based on a data set. So the ultimate overarching goal here always was that we could have the community help us write interfaces for the data that we start incorporating into MP. All right, keep digging deeper. In terms of now AWS, what the choices we made was that we wanted to use infrastructure as code from the beginning, from the ground up. So we're using AWS CloudFormation to basically do the entire shipment process and deployment process, building process for us based on a simple Git push on the GitHub side. There's a longer list of GitHub repositories that we now push to and maintain, but As a first step in the CloudFormation pipeline, the source is being pulled from GitHub and put on an Amazon S3 bucket as an artifact. The second stage of the code pipeline builds or maintains the cluster, the VPC, the network load balancer, the databases we need for user management, Elasticache, all those base resources that are required for a web stack. And then the third iteration basically takes the templates that are stored in these GitHub repositories and the code for our web services, uses AWS code build to build Docker containers, and also in this process we're tagging the images with the versions and also set Datadog environment variables. That's for later, something very important to keep track in terms of monitoring later. We make use of Kong a lot. I'll talk about this, but this stage builds the Docker containers and the web services and pushes them out to ECR. And then during the deployment phase, we're using AWS Fargate and tasks on AWS Fargate. So a lot of this is standard, I would say, standard AWS cloud. We are growing more on the Lambda side, so some of the tasks that we have are becoming on-demand serverless functions, but so far we've been pretty classic in terms of setting up our infrastructure. So the code pipeline basically looks like this. As I said, these are the GitHub pulls from the repository, maintaining the base resources, parallel build our Kong abstraction layer. That's the service that sits in front of the two backend services, which are MP-Contribs and the Materials project, the main website, and then deploy the two backend services and Kong. One note here on how we deploy Kong and the backend services. Kong itself sits, as I show in a minute, sits behind a network load balancer, so it talks to a listener. And for that, we use the standard ECS blue-green deployment to basically switch between a listener and a test listener and redirect traffic automatically. But then for the backend services that are sitting in a separate subnet, we're using Kong to basically switch from one service to the other as we are making blue-green deployments. So what does that overall scenario look like? Basically, all of our stack and the network load balancer in AWS sit behind Cloudflare. So we're making use of their services of fighting off attacks and proxying traffic to our network load balancer. We're also using log push directly from Cloudflare to Datadog, which is a big aspect of logging later. As traffic comes in through the internet gateway and our network load balancer, we have a public subnet where the Kong instances sit. Those instances are responsible of routing traffic to the according upstream services. And then in a private subnet, we basically deploy the backend services, APIs, webends. It's in total, I think, 7 or 8 services that are running to make up MP. And then the APIs that sit in the private subnets talk to MongoDB Atlas through a peering connection. What we're also working on is getting a direct site-to-site VPN connection to on-premise. As I've talked before, we have resources sitting at NERSC that would be nice for us to connect to, but that's not data we would move into the cloud and would also not need up 24/7, but it happens occasionally that users might want to access resources and DOE facilities, and for that we're exploring setting up site-to-site connections to DOE facilities. Just a word on Kong to explain what that abstraction layer does. Basically on the left, this is the standard picture that Kong basically uses to explain its services. We have users or services go through a layer of plugins that sit on top of the backend services. So the backend services are basically just the naked containers. They do the functionality that they need to do, but they don't do any user They don't do any authentication, no ACLs, rate limiting, all that stuff is done in Kong. The plugins that we use in Kong particularly are for rejecting bots, for cores, tracking metrics, request size limits, the session management for users, API key management and keys, and then group managements for authorization. So all of that happens before any of the traffic even hits our backend services in the private subnets. Kong also has what's called upstreams. So these upstreams are the backend services and their IP addresses, basically, and a ring balancer basically walks over these IP addresses, which are called targets, to kind of find the ones that are healthy, does health checks, and then routes the traffic to the according Fargate IPs and ports. One thing we had to develop for Kong was a somewhat easier login plugin or session plugin to connect. Basically, what we wanted is a simple social OAuth and email login platform. We don't actually use much user information. All we need is an email address, so this can be pretty simple. And we've decided to use an OAuth proxy server called Grant. And that proxy server is capable of talking to a long list of OAuth providers. And we added on top Portier to allow email logins as a self-hosted service. And both of these basically talk directly to the behind the scenes to the Kong admin API, generate consumers, set their API keys, and initiate their sessions directly in Kong. So once that login process has happened, Kong basically knows right in the Nginx layer whether a user is authenticated or not, and this becomes a really fast solution. Okay, so as I said, we're running the Kong gateway in front of the backend services, and the backend services are sitting in two separate subnets. Basically, the production one is running, and the other subnet is free. And then once we deploy in the one that is currently free and flip the switch in Kong to go from one subnet to another. So it's kind of a hybrid blue-green between what AWS would standard do with a network load balancer and then Kong in front of the backend services. You can see that each of the tasks basically Optimate, Next-Gen Web, and Next-Gen API, Next-Gen Countries API, those are our 4 services, but we're also running a logs container and a Datadog sidecar container in that same task. What does that exactly look like? And now we're getting into the Datadog part in terms of monitoring those microservices. As I said, we're using AWS Fargate. The application containers I've just described, they're sitting in a list of AWS Fargate tasks that we can scale as needed, and then the Datadog agent runs as a sidecar container within those tasks. It tracks the traces through a dedicated port. It talks to the ECS task metadata endpoint that is, I think, available since Fargate 1.4 to kind of collect metrics and information about the containers. And then it also applies auto-discovery labels depending on what kind of container it's running. So that's basically all happen almost automatically as we put the sidecar container for Datadog in the task, and then the logs are taking a separate route through AWS FireLens to Datadog. Both the Datadog agent and FireLens are talking to the Datadog servers through their dedicated VPC endpoints, and that's one of the things that has gotten me to Datadog very early, because I was particularly looking to not route traffic through the internet and pay in addition for egress that is just logging. As I said, we're a small DOE project compared to other, within DOE we're pretty big, but compared to AWS world, we're small, and traffic and egress matters for us. So we've been very careful that with VPC endpoints, I can control the expenses, I can control their uptime, but I don't get any surprises in terms of processed data volume or processed traffic. And Datadog made that possible, so that's one of the probably big takeaways for me why Datadog won the race. So both these, like the logs and the traces, are making their way to the US East deployment of Datadog through the VPC endpoints. And then from then on out, all logs can go into a Livetail on the Datadog platform. We're generating metrics. Part of these metrics also is our Cloudflare metrics. So I set up a custom Cloudflare metric that keeps track of the requests and bandwidth and durations directly from Cloudflare, so I can compare what Cloudflare says versus our backend services. And also very importantly, since we're using log push from Cloudflare directly into Datadog, we need to control our costs as far as Datadog is concerned, and for that we use index exclusion roles and index and only include in indexes what's actually important for us. One additional important feature always was for us that we could look at our historical data without having to change platforms, and Datadog makes that possible through rehydration, what we call rehydration. So our everything that goes through Datadog also goes to an S3 bucket archive, and we can at any point pick and choose log files from S3 and rehydrate the logs and look at the same interfaces that Datadog provides to debug. So we started to work with this a little. This is not by any means done yet. I'm basically just in the process of setting this up with big screens in our offices so we can always have Datadog running up there and see what our websites are doing. This is just the start in terms of like, okay, well, how many data logs are we how many logs are we ingesting? You can see that there's a lot more coming from Cloudflare, but the index exclusion roles are just like boiling it down to what we need. And then all the backend services are also logging to Datadog. It's kind of it shows me what kind of changed over time and in terms of logs. There's a log stream that I can keep looking at, and I've made a few graphs where I basically look at the health checks and the success rates by host category, see whether what the bandwidth and our cache hit rate is, and then also keep an eye on our real bytes and average durations, all by different host categories. The host categories are something that is also set by Datadog parsing. I'll talk about that in a minute. There's custom processing pipelines that I set up just to make sure that I get I can enrich the logs that are coming from Cloudflare with things that I need to do Datadog analyses a little easier. We're also keeping an eye on CPU and memory, right? For our containers, this has always been a little tricky because as scientists, we sometimes don't really think about memory or other things, and we just keep adding and our interfaces get heavier and heavier. So there's definitely room for improvement in terms of how much memory and how much resources we use in the cloud. As a comparison, on the current legacy website that we're running it on-premise at NERSC, and those NERSC machines, we have 10 parallel machines running that have, I don't know, hundreds of gigabytes. So we never had to like really look at memory and be a little bit more careful. And Datadog helps us keep our costs within limit here and optimize in a way that doesn't sacrifice performance. Also one thing that we like a lot are the APM traces. So basically we out of the box without actually doing much other than getting the Datadog sidecar agent running is getting our API endpoint split up by endpoint with the latencies, with the error rates, with the number of requests by endpoint. So at any moment, if anything happens on our website, we would pretty immediately know what's going on. And internally, we immediately know each of these endpoints has all their little quirks, and we know what the culprit probably is just by looking at some of the latencies when things were not going as expected. In terms of processing pipeline, as I said, I set up a custom kind of unified parser for Python, Junicorn, and Supervisor-D. Most of it is standard, but some things that I ended up doing is the, I can't find it here right now, but for Cloudflare is basically setting up separate host parsers and host categories and setting up separate URL path categories. So instead of having metrics that are basically tracked by each and every possible path, we're categorizing them by root level path, and we're categorizing hosts and compiling hosts into multiple ones so that the metrics are not getting too expensive. We've also enriched Junicorn access logs with header information from Kong. So when Kong sends the requests up to the back end, which are all Junicorn servers, that those headers are forwarded, and I can tell by the request logs what user it was, what other important headers like bandwidth and bytes processed were, and that stuff helps then kind of drilling down of what a user is currently experiencing. Okay, and as a final slide on the cost overview, and those numbers are, I'm not sure whether it's a surprise or not, but again, like when we started, I think I started with AWS 3 years ago, 2.5, 3 years first when I started with AWS, and at that point we were still very much in like, okay, we're going to run this on-premise and basically run our own. It's going to be way too expensive to do it in AWS. That's always been the prevailing argument, because our current traffic on our legacy website is about 4 terabyte a month that we disseminate with our API, and just 4 terabyte with egress costs would already blow our budget that we had anticipated, right? But time has moved on. Things are getting cheaper as demand is growing, and if you architect it right, I think we're in a really pretty happy place right now. Our biggest expenses is MongoDB Atlas. That's also showing up on our AWS main payer account. So we're about at like $20 a day for MongoDB Atlas. We're using a savings plan for compute usage, which makes a big difference, gets our costs down by another 60% for the compute part. That adds about, I think, 10 a day. Then some on-demand Elastic Container Service part in red, that is when we're spinning up a new deployment, then these run on demand. We have some S3 storage, about 5 or 6 terabyte of charge densities that are basically just objects that we disseminate through the API. The VPC costs, and then others is what currently also includes traffic and also includes Datadog. So I think our Datadog costs, even though they're not shown here, are around $5 a day. But all of this will scale, like most of this will scale a little bit with traffic, but we're not expecting it to explode. Okay, so as a summary, and I'm actually very well in time, I think, MP is one of the leading research platforms in open source codes for material science. I've shown what kind of science we do. We've underwent a major transformation for our data and our compute from what we had on-premise DOE supercomputing resources, namely NERSC, to cloud and infrastructure as code. Datadog really helps us to have end-to-end visibility. There's no blind spots, and I couldn't list the examples of how many times in the last half a year when we did that, we found errors that we wouldn't have found before, or we found them in like a minute. Just before I gave this talk, actually, I was looking at stuff and was able to get the site up and running again because I had Datadog. So I know it's helping us a lot in terms of monitoring. And then both Datadog and AWS have made that transformation really achievable, because in the end, we're a very small team of scientific software engineers, and we have limited resources with the budget, the time. And as you said, I think it's me as a computer systems engineer. We have 2 software developers, and that's basically it. We'll do all this. Okay, thank you very much. We have a lot of time for questions.
If there's any questions, please go up to the microphone.
Hi.
Oh, that's not on. There we go.
No, it's on.
Thanks for that. That was great. What else did you look at before you chose Datadog, and what other than the VPC endpoints helped you choose?
That's a very good question. We had New Relic on the radar. I think for what we actually used New Relic too for a while on the legacy website. For me, the biggest factor was how easy it was to work with AWS and knowing that VPC endpoints are a factor. I think the first time I looked was early 2020, just when Fargate 1.4 came out. And also the other aspect, and it's not quite there yet, is NPM, so network monitoring. But NPM with Fargate is not quite, I think, there yet, and there's some bottlenecks that are missing. But that's the other big one where I'm in the hot seat. I really would like to see that, but I know it's difficult. So these two were the ones that I kind of looked for specifically, and the VPC endpoints for me sold it because I knew I could just relax and set this up. I'm sure there's other services that would do the same, but then maybe one thing I can also, and one of my coworkers was really intent on error tracking, so automatically categorizing error tracking because we were using Sentry. So kind of, making sure that we don't lose the capabilities we had in Sentry to also do error tracking, and Datadog does that. So very good question, though.
Are you allowed to share with us about how much Datadog was costing you for your workload that you shared? And then I have a second question. Do you have a reason why you chose Cloudflare over CloudFront?
Yeah, good one. So for Datadog, I think our estimate right now is, if I include everything, would be 150, 200, maybe up to 300 a month. That's my current gut feeling. I think at the moment we are at, without traffic scaling as much yet, because we're slowly scaling up and see what the efforts are. We're at like $5 a day, so $3 to $5 a day. But yeah, you have to be careful with index inclusion roles, and it's not like you can just throw everything at Datadog and hope for the best. But it's all in place, so it's so far so good. Yeah. And then for Cloudflare versus CloudFront, one reason just was we've had Cloudflare in front of our legacy website, so there's a lot of existing experience with that. I also felt using CloudFront from like a 10,000-foot experience a little bit too hard to get going. And the third thing I would maybe know importantly is that's why we also have Kong is vendor buy-in, right? Like we've been a little careful not to get too much into specific services that we would then have trouble transferring to other cloud providers. Because it's definitely happening that the DOE and others are negotiating with different providers, right? So there's more to than just like, yes, how much could I possibly solve with AWS? How much could I possibly solve with Google Cloud? So, yeah, good questions.
Yeah, and Patrick, I really liked all the architectural drawings that you had up there. I'm wondering about you were setting your data retention policies using Datadog, right? You had a 15-month status, I think I saw up there for some of the logs. For that data that's being rehydrated,
yeah.
Where is that data living when you're not needing it? And do you decide that, or is that decided through policies that you write in Datadog?
It's actually pretty simple. Datadog has different endpoints that I could send the data to directly in their platform. We send it to S3, so it's a simple S3 bucket, and it would rehydrate directly from S3. Yeah, on the Cloudflare side, I can set up in log push which part I want to send to Datadog. So I don't have to send the full log, like WAF rules. Did it hit or did it get blocked, right? So I have enough control over how much data actually ends up in the S3 bucket. The only thing I would have to do on Datadog side is what I include in the index, and that's what you get charged for, right? Anybody? Oh, she's waving. You want to ask a question? I don't see anybody else. Thank you.